Hello, Year 10. This is a practice lesson on 6-marker questions. So a 6-marker question is a very particular style of question that you will come across within your GCSE exam. It tends to be an extended answer. It will involve some data provided, but it will also have some of your own knowledge required to get you to the higher levels. Now, you will see as we do the 6 markers that there is a set format to the mark scheme that you can be a level 3, a level 2 or a level 1 answer. A level 3 can be worth 5 or 6 marks, a level 2 can be worth 3 or 4, and a level 1 can be worth 1 or 2 marks. And which level you get to depends on not only the content and your analysis of the data provided, but the quality of what you are writing. It's the one area of the course where we're looking at things being written in a very logical manner, in a very clear manner that sequences effectively. So there are some parts of this that are not 6 markers. I would like you to pause when you get to the questions. When you've tried the questions, then go ahead and listen to the answers. On the 6 marker, I want you to stop for at least 6 minutes because you would get 6 minutes in the exam. I would like you to wait for potentially up to 10 minutes where you can really think about what you're doing. And I've got no problem at this stage with you finding answers. So do go online, do go to the textbook, do take a look at old notes to see if you can find ways of building up your answer to get to the 6 marks. So let's begin with the first set of questions. Pause. Okay, so a lot of multi-choice here. You can see that we've got a periodic table. All of our answers are going to come from J, L, M, Q, and R. And you need to read very carefully. You need to tick one box in each case here. B has got 2 answers, but in all of the others, if you tick more than one box, you then forfeit that mark. So we're taking a look first of all at which element has 4 electrons in its outer shell. Well, I'm going to add some information here. I'm going to add the group numbers. You can see we've got group 1 and 2 on the left hand side. We've then got that big chunk in the middle that are not numbered. That's the transition metals. And then we've got groups 3 to 8 on the right hand side. So then we take a look at what might cause it to have 4 electrons in its outer shell, or where we would look for something that has 4 electrons in its outer shell. And the answer that we're looking for here is J. It's in group 4. The group number is equal to the number of electrons in the outer shell. Now the next question, which 2 elements in figure 1 are in the same period? Periods we are going to number from top to bottom. They are the horizontal lines in the periodic table. So I've numbered them there, 1, 2, 3, 4, 5 and 6, and we're simply looking at 2 that share the same period. And in this case, it's M and Q. You could write those in any order and you would still get the mark. Which element reacts with potassium to form an ionic compound? So for this, you have got to have a little bit of residual knowledge. You need to know that potassium is a metal. So you need to know that you're looking for a non-metal that will react with it. And there's actually only one option here that you can use. We are looking for, as I've said, the ionic compound. So we're going to go for Q. Q is group 7, so that would actually be a bromide ion. That would be bromine forming a bromide ion. But it will gain electrons, whereas potassium, which is in group 1 with L and R, would lose an electron. Okay, so Q for that one. Which element forms ions with different charges? Again, you've got to be aware of some very key facts here. The area of the periodic table where you find elements that form ions with different charges is the transition metals. So when you are looking for that, it's the chunk in between the groups, as I said earlier. So that takes me to answer M. And finally, which element has 3 electron shells? Now you will remember, hopefully, the first principal energy level holds 2 electrons, second holds 8, third holds 8, and we go as far as 2 in the fourth. Calcium is the biggest that we go. Now the one that has got 3, it's actually done by periods. So we can see that L would have 3 electron shells. It's actually got 2, then 8, then 1. If you were looking on the periodic table, you would see that it's sodium. Okay, 6-marker question. A lot to think about here. Do read it carefully. Particularly, I am going to point out to you, Figure 3 shows the periodic table published by Dmitry Mendeleev in 1869. So you're provided with his early version. You are not given Newland's table. There's an expectation that you can remember elements of it. Do find a copy of it if you want to for the purposes of this lesson. So I'm going to ask you to pause for at least 6 up to 10 minutes. Pause. Okay, so I am going to show you how we actually assign the marks, first of all, in terms of levels. So you can see here for a level 3, 5 or 6 marks, you have a judgment, it's strongly linked, and it's logically supported by a sufficient range of correct reasons. To get a level 2, you might have some logical linking, and there might be a simple judgment. And in level 1, you might have a logical link, but you've made some relevant points. So with that in mind, what sort of things are we looking at? Remember, this is a comparison. It's a comparison of what we see here, Dmitry Mendeleev's table from 1869, and Newland's table. Well, if you're doing a comparison, it makes sense to look at what similarities there are. And in terms of the similarities, I've just pointed out there what I said at the start. This is Mendeleev's table, not the current table. And we're remembering Newland's table. In terms of the similarities, both have got more than one element sharing a place. So here I've used one example. I've got molybdenum and technetium that are sharing a box, but chromium and selenium are as well, vanadium and astatine, niobium and antimony, zirconium and tin, yttrium and indium. All of those pairs are sharing here. There's zirconium and tin just highlighted. And I've highlighted in purple there to see what we can see. Now that happens in Newland's table as well. I've also highlighted in yellow another similarity. Elements are grouped together with similar elements. So we can see in Mendeleev's table, and this happened in Newland's as well, lithium, sodium, potassium, rubidium, current group 1 are all grouped together. Fluorine, chlorine, bromine, iodine, all current group 7 were and are grouped together. In Newland's table, Mendeleev's old table, and actually in the current periodic table. I've actually taken this smaller now because I realised there was a lot more to write. The other similarity, there are no noble gases included. Now that's a question in exams in itself. Why would you not have a noble gas? Say the answer to the screen now. Okay, what I'm hoping you said is they haven't been discovered yet. And we've got them ordered by atomic weight. Now that is what Mendeleev did initially. What I hope you remember is that it's now done in order of atomic number. Now in terms of the next stage, the next phase of this answer, we want to talk in terms of a comparison about which one is better. And Mendeleev's is better. That's why we use it now and not Newland's. But why? Well, he left gaps for undiscovered elements. This is a really common question with an equally common answer. I've given 2 examples there where he put question marks. He knew there'd be an element. He didn't know what it was yet. But he went further. In fact, no, sorry, I'm going to come back to that in a second. Newland's actually had a lot more non-similar elements grouped together. Now, you would have to remember that. That's not provided within this question. In terms of the third stage of this, why Mendeleev's table was accepted, we've said it was better, and we've got the answers there. But why was it accepted? He predicted the properties of missing elements. A really common example here is germanium. It hadn't been found yet, it hadn't been isolated, but Mendeleev said there will be an element that is going to be discovered. It will fit here in the periodic table. This is what it will look like. This is what its melting point will be. This is what its density will be, etc. And when it was discovered, everything he said was correct. So that gave people confidence that he had come up with a working table. And as I've said, I've sort of alluded to this already, but once those elements had been discovered, they fitted where he said they would. So, in terms of going back to the green box here, the judgment here is that Mendeleev's table is better. And if you have explained why it's better, that takes you into level 3. If you have taken some of these ideas and linked them together, but not come up with a strong judgment, or justified your judgment, you move into level 2. And if you've picked out some of the points, like they are sharing or we've got similar elements together, it takes you into level 1, but it doesn't really take you much further. So that's the end of question 1. We're going to move on to question 2. Pause. And let's go through. So we're looking at numbers of protons, neutrons, and electrons. A relatively straightforward question to begin. Number of protons is equal to the atomic number. I've used colour coding here to highlight it, so it's 13. I'm going to do electrons next, because in an atom, the number of protons is equal to the number of electrons. And finally, number of neutrons, you have the mass number and subtract the atomic number, which takes us to the answer 14. In terms of why aluminium is positioned in group 3, well, it's got 13 electrons, we know that. Its electron configuration is therefore 283, and therefore it has 3 electrons in its outer shell. On to the second and final 6 marker. Again, read this carefully. Give yourself between 6 and 10 minutes to do it before you press play again, and then go through and review your answers. I've highlighted down at the bottom how the levels are determined. So level 3, detailed and coherent comparison is given, demonstrating a broad knowledge, understanding of key scientific ideas, thorough links between points raised, and you are using sufficient examples. Similar to what you can see on the previous one. Level 2, reasonable knowledge and understanding, comparisons made, maybe not articulated fully. Level 1, you're making simple statements, you're showing a basic knowledge, but you're not necessarily making comparisons. And I've started to go through my answer here because what I'm going to do is try to think about the differences, similarities and differences. And actually, in the comparison, the differences are key here, and there are lots of them. Now, we can break them down into physical and chemical properties. I'm going to start with the physical properties. This is all knowledge that we are going to need to take into the exam. Melting point. Group 1 metals have a low melting point. We can actually see that when we do the reactions. When we ignite potassium, for example, in air and get the lilac flame, it actually melts when we burn it. We know that transition metals generally have very high melting points like iron and zinc and copper. Density. Well, transition metals have got a very high density. Group 1 have got a low density. And again, we know that because they float on water. It takes us back to that chemical reaction that we saw where we're comparing reactivity. And strength. Again, we know that transition metals are strong and they're hard. That's why they're used a lot in the places they are. But we know that group 1 metals are soft. They can be cut very easily when they're being prepared to react with water. And you'll have seen that within your lessons. So we've got 3 physical properties there. Chemical properties, reactivity. Well, I've already touched on this. We know that group 1 metals are very reactive. We know that even in water they will react. Potassium actually ignites just on contact with water. But we also know that transition metals are comparatively not very reactive. Iron will rust in water over time. Copper is used in water pipes because it doesn't react with water. So we've got that comparison. Catalysis is taking us up to the next level, and this is touched on more and more over the 2-year course. But all catalysts that we discuss are transition metals. So we use iron in the Haber process, for example. Group 1 metals are not used as catalysts. Ions, well, we can use the information here actually to answer this one. Group 1 has fixed charges. Group 1 forms ions with a +1 charge because they all lose 1 electron. But transition metals have variable charges, and we can see that by, for example, iron can form 2 different oxides. To get FeO, iron has a charge of +2. But to get Fe2O3, iron has a charge of +3. But as a simple fact, we remember that transition metals have variable charges on their ions, and group 1 have fixed charges on their ions. If we look at colour, transition metals form coloured compounds. Copper sulfate is a really vivid blue, you'll remember, whereas group 1 forms white compounds, or colourless compounds, or colourless solutions. So we've got to remember that comparison. And the key thing on this 6 marker is that the vast majority of what you need to answer it comes from your own knowledge rather than the table. We get melting point from there. We can do the comparisons that's provided. We can use the variable formulae to know there are variable charges on the metal ions, although there's still a level of knowledge there. But all of the rest of this comes from what you have learned and retained. And that's why revision of these facts is so vital. So that brings us to the end of today's lesson. These 6 markers will be something that we will look at again and again and again. So consider this an introduction to them, and we will continue to build the knowledge and skills as we go through the course when we return to in-school teaching very soon. Okay, thank you for listening. Goodbye.